Let's record then. In this lecture, we are going to continue our discussion about practical issues with working with time series, and this is going to be about forecasting. So the cornerstone of everything that we are doing this for. So we've covered linear time series models. We know that there are two types: AR models, MA models. We know that there is a generalization of them in the form of ARMA PQ model, where we have the AR part, MA part. Yeah, so minuses disappeared somehow. I don't know why, but still. Regarding the estimation, so this is the theoretical part, right? So the model parameters and how the model must look like in mathematics. So this is the population world. Now we are going to the data world and how to feed the data into the model. There is a Box-Jenkins methodology that helps us doing this. We identify which model suits better with the help of sample ACF and PACF. Then, choosing the model, we estimate the parameters either with MLE or OLS, and then we perform diagnostic tests, whether the residuals are correlated using ACF and PACF again, using Lundborg statistics, using Breusch-Pagan statistic, and so on. So what's next after we estimated the models? So next is the practical use. Why we are doing all this? Because we want to forecast, because we need to know what is going to be in the future, or at least we want to predict what is going to be in the future. Before proceeding to the forecasting itself, we need to solve the problem that appeared in the last lecture. The problem was with that we have seen that two models passed the diagnostic tests. So in our case, AR1 model and MA2 model passed the diagnostic tests. So what we have to do in such case? We can answer the question which model yields best in sample fit. So what does it mean? It means which model better fits the observed data. We know that in cross-sectional econometrics, R squared was the measure that told us, that answered us this question. So with the help of R squared, we answered what is the fit of the model. In the case of linear time series models, R squared is not always useful for many reasons. And usually we use two information criteria. So one information criterion is Akaike information criterion, or in short AIC, AIC. And the second one is Schwarz or Bayesian information criterion, which is for short called BIC, BIC. So what these criteria are about? So all of them compare the residual variance against the number of estimated parameters. So they penalize, they punish the model for additional parameters, and they increase with the precision of the model. So this is something similar to adjusted R squared that we have covered in econometrics. So let's see how these two criteria are constructed. So if we have ARMA model and we have K parameters, P plus Q plus 1. So AIC is computed as N, which is the number of observations, times the natural logarithm of the estimate of sigma squared, which is the variance of residuals, plus 2k. 2k is the number of parameters plus 1. So sigma squared head is the residual variance from ARMA model. So residuals squared and then sum. the values of P and Q should or must minimize IX. So such values of P and Q that minimize IX must be selected. So basically, this is also an algorithm how to choose the appropriate P and Q. Just automatically, we are looking for such P and Q that minimize this criterion. So why minimize? This should be minimized because it has variance inside, and variance must be minimized, so we want variance to be minimum. So 2k is also must be minimized because we want to be the model as simple as possible. We don't want to expand the number of parameters. So the minimization is done by variant P and Q. This is simple. So basically there are some automatic algorithms that just can give you such P and Q that IX is minimized. Now the second one, Bayesian information criterion. It has similar shape. So the first term is the same, n logarithm of sigma squared. But the second term punishes the model stricter with the increase of parameters. So it's k times ln of the number of observations. So here we had just 2k. So all the time, every additional k just twice increase the I. But here, the more observations the model have, the larger is going to be this ln n. And k is gonna penalize the model stricter. So for n greater than 8, ln of n is going to be greater than 2, so big penalizes additional parameters heavily, more heavily than I. And again, the model order is going to be selected where big is smaller. And usually, big proposes the smaller model than I. Smaller in terms of the number of parameters. Another reason why big is better than IC that it is a consistent selection criterion, so the true model is selected when n goes to infinity. So remember that consistency is when the probability limit of the parameter coincides with the population parameter. So let's see an example. In the last lecture, we estimated two candidate models for Russian GDP growth. One was MA model with the following parameters estimated, and another one is AR1 model with the following estimated parameters. ACF and PACF sent us the controversial signals, so we don't know which one to choose. Now, let's see which model has the better in-sample fit. So which model has smaller information criteria. So the information criteria are always given here in the regression results. So you can always find them here. There is another information criterion, also Hanna-Quinn. We are not considering it, but basically the logic is the same. So there are three coefficients basically, Hanna-Quinn as well. So these are the criteria for MA model. And these are criteria for AR1 model. So obviously, criteria for AR1 model are smaller than criteria for MA2 model. So which means that AR1 has better in-sample fit. And we have several reasons why AR1 model is better. First of all, AR1 model is good because we are able to, well, better work with it. Second, AR1 model passes this test with the help of information criteria. Third, it is simpler. It has only two parameters to estimate instead of MA model. So and the forecasting is easier. So that's how we choose the models if we have a lot of them as a candidate models. Now, talking about forecasts. We want to use, as I was talking several times, we want to use ARMA models to forecast future values of the series. So in the further discussion, we assume that we know the true model parameters, current and past realizations of epsilons and y, because, well, first, again, we need to build everything based on the theoretical models, and then we would go to the estimated values, and we will talk about how to estimate the forecasts. So suppose we want to forecast the value of a variable yt plus 1. So the forecast is going to be based on a set of variables observed at date t. So this is xt, because xt is a set of everything that we know till today. For example, xt can consist of a constant yt and yt minus 1. So this is a set, this is the vector of variables that we know in order to make this prediction. Let's denote the forecast as y star t plus 1 given t. So given t means that we use everything that we know up to time t. And this is going to be the forecast of yt plus 1 based on xt. If you want to evaluate the quality of the forecast, we want to compare the actual realization. So one period passes, so the time goes by, we are in the future, and we take our forecast, this one, and we compare this forecast with the actual realization of the value. And when we compare them, well, there is an error, the forecast error, how far the actual realization is from the prediction, the forecasted value. We introduce an object that is called mean squared error. So mean squared error is the expected value of a squared forecast error, because this is the forecast error, right? The forecast error is a random variable. At time t, we don't know what would happen in the next period. Therefore, this forecast error for us today is a random variable. This random variable is squared and taken the expected value, and then we call this mean squared error of our forecast. And what do we want? We want to build such forecast that minimizes this mean squared error. Of course, we want to be our forecast as close to the future realization as possible. And the forecast with the smallest mean squared error is just a conditional expectation of yt given x. So the forecast must be computed as the conditional expectation. And we know what is the conditional expectation. This is just, in terms of cross-sectional econometrics, this is just some function of yt plus 1, when yt plus 1 depends on yt minus 1, So we spoke about conditional expectations in the form of linear regression, nonlinear functions, and so on. So in our case, this conditional expectation is exactly AR or MA model. So linear function of x. So in our case, for example, if you have AR1 model, this one, what is going to be the one step ahead forecast? So y star t plus 1 given t. So our prediction for the future given the current values known for us at the period t. So this is going to be expected value of yt plus 1 given yt. This is expected value of the following expression given yt. And so expected value of a constant is constant. Expected value of yt given yt is yt times constant. Expected value of the future error is 0. So we have this. So this is our forecast, one step ahead forecast for yt plus 1. Well, basically this is simple. The one step ahead forecast error is going to be the deviation of yt plus 1 from the forecast. So we are taking this minus this, and we have that the one step ahead forecast error is going to be epsilon t plus 1. So don't confuse. This is E, this is forecast error E, and this is epsilon. The epsilon is going to be the innovation at the period t plus 1. So this value of a white noise at the period t plus 1. So this is so-called unforecastable portion of yt plus 1, given the information available in t. So what we are not able to forecast. So the variance of one step ahead forecast is going to be the variance of this error. So this is going to be the variance of our white noise, and this is going to be sigma squared. And the most important thing for any forecast, it is not possible to report just a forecast. This is not practical. This is not professional. You always need to report the forecast plus 95%, at least 95% confidence interval for your forecast. So you need to say, well, we are 95% sure that the future value of yt is going to be between this and this. And well, with the help of our knowledge from statistics, we know that if we assume that white noise is normally distributed, we can build the 95% forecast as following. So this is just our expected value of yt plus 1 plus and minus 196 times the square root of sigma squared. Sigma squared now is the standard error of the forecast error. So everything is very similar to what we know from the past. For example, let's see how it works in practice. So I don't have it on slides, but we can go together from the through some steps. So here we have AR1 model. Let me open the Word. So we have AR1 model, which is yt equals 09353 plus 06162 yt minus 1. So this is not yt itself, but this is yt hat, of course. It's going to be hat yt. We know also the estimate for sigma. We know that hat sigma squared is 23.563, like this. So now we need to know, well, if you want to build the forecast for t plus 1, again, this is going to be the estimate of the forecast because it's not the forecast itself. We don't know the true values of the parameters, but we can do something like this. So this is going to be 09353 plus 06162 yt. So now we need to know what is yt. Let's go to the data. That was something like 5%, let's say. So assume that YT that GDP growth was 5% in 2021. So YT equals 0.05, let's say, or 5%, doesn't matter. So in our case, the forecast one step ahead forecast for 2022 is going to be this. So we just plug the value of the past realization 0.05 into the model, and we have 0.6162 times 0.05 plus 0.9353, so 0.96611. So well, something strange, isn't it? Well, yeah, these are not, this must be in like 5. It's not 5%, yeah, just 5. 0.6162 times 5 plus 0.9353. So yes, 4.0163, like this. Percent. Right? So, but again, if you give this forecast without any additional information, this is going to be very weak and not practical. So we need to build a 95% confidence interval. For the forecast. And this 95% confidence interval is going to be built very easily. So we just take our forecast plus minus what? Plus minus 196 times the square root of sigma squared, this 235563. So 235563 to the power of 0.5 times 196 plus, well, this is our deviation. So basically 40163 plus minus 95128. You see that the spread is so large because of sigma squared. Well, our forecast is gonna be 40163 minus 163 minus 95128. So from minus, so basically the forecast, the GDP growth forecast 22 is from minus 549.65 to 401.63 plus 9.8 to 13.5291. Well, again, this is not very precise forecast, right? So the spread is so large from minus 5.5 to plus 13.5, so almost no use of such a forecast. Therefore, we need to improve our model somehow. But basically, as a principle, you can use this approach for any forecasts. Now we need to kind of concentrate better on some practical points. So probably we need to concentrate on some particular period. We probably also can build the model with the help of quarters, right? Because the quarterly statistics for GDP are also available. But everything this is out of the scope of this lecture. So my goal is just to demonstrate you how to work with the simplest possible cases if you want to perform something similar in the future. So questions, maybe you have something to ask here. Fine. Two-step ahead forecast. If you wanted to build the forecast in 2021 for 2023, so what is going to be the two steps ahead forecast? The logic is the same. Y star t plus 2 given t is going to be the expected value of yt plus 2 given yt. So basically, what is the model for yt plus 2? This is phi 0 plus phi 1 yt plus 1. So now we don't know what is yt plus 1. We need to plug the expression for yt plus 1 here. And finally, like recursively, finally we have the following expression. So phi 0 times 1 plus phi 1 plus the following coefficient squared yt. So the error is t plus 2, which is the difference between the actual yt plus 1 and the forecasted yt plus 1. So the actual yt plus 1, we plug the formula for the model for this. The forecasted yt plus 1, we plug the model for this. And then after subtracting everything, we have epsilon t plus 2 plus phi 1 epsilon t plus 1, something that looks similar to MA model. And the variance is going to be the variance of this expression, which is sigma squared plus phi 1 squared sigma squared, or just sigma squared times 1 plus phi 1. Again, 95% confidence interval is built with the help of this conditional expectation plus minus 196 square root of this error, the forecast error. So this and these are identical, right? So I just took sigma squared out of the bracket. Again, let's see an example. The two-step ahead forecast for 2023 is going to be the following. So basically this is yt plus 2 given t. Well, we can do the following. So we already have this expression and we plug here our forecast for 2022. So already computed forecast, this one. So 40163 times 06162 plus 09353. So this is 34101, let's say. And the 95% confidence interval for this forecast. Let's compute it as well. So this is 34101 plus minus, and now we are not only taking sigma squared, but sigma squared must be multiplied by 1 plus phi 1 squared. Phi 1, which is 0.6162, like this. So what do we have? 34101 here. 06162 squared plus 1 times 235563 square root times 196. So this is 11, 11, 17, 38. So you see that the uncertainty expands, right? So the further in the future we are trying to look, the larger is the uncertainty about this future. So finally, the GDP growth forecast for 2023, again from 2021, right? So this is important. So we assume that we are in 2021. So 2023, from again 2021 is from, so 341.01 minus 11.1738. So it's from minus 7.77637 to 341.01 plus 11.1738 to plus 14.5839, something like this. So that's how we work with the forecast for AR1 model, for example. If we are using AR2, AR3 models, so the logic is the same, but well, maybe the mathematics are going to be a bit more complicated. Yeah, so jth step ahead forecast is going to be built similarly. So we have the following expression for yt plus j, the following expression for the error term, which is just the structure on the white noises from every next step. And finally, this is the variance, and 95% confidence interval is going to be computed similarly. So this is just a generalization for any step ahead forecast. Now, how do we do forecasts with MA models? MA models are less kind of interesting for building the forecasts. So one step ahead forecast for yt plus 1 is going to be this. So this is going to be mu plus theta 1 epsilon t. So epsilon t must be computed from the past. So you know what kind of, we need to go back one step, produce a forecast for today, measure the difference between forecast and the actual observation. This is going to be epsilon t, which is kind of unobserved, but can be estimated with the method I explained you. So one step ahead forecast error is going to coincide with epsilon t plus 1. This is the same as for AR1 model. Variance is going to be sigma squared. And again, the confidence interval would be computed similarly to AR1 model. For two steps ahead forecasts, we immediately converge to mu. So for MA model, this is very simple. After we pass the orders of MA, the forecasts would converge immediately to mu. So just to the mean value of this series. And the error is going to be just the leftovers from the model, so these parts. So the variance would increase, of course, and 95% confidence interval would also expand. With the j step ahead forecast, the forecast is going to be still mu. This is why I said that this is not that practical, because you will have a flat forecast forever. So your forecast is going to be constant with MA model. Nothing kind of interesting and special regarding the dynamics of the forecast. You saw that in AR1 model we had the dynamics, right? So the forecast for the first period is 4, for the next period is 3.4. For MA model, this is going to be flat, constant forecast with no any dynamics. J step ahead forecast error would be also this, and finally the confidence interval is going to be the same as for two-step ahead forecast. This is interesting. In AR1 model, the forecast error expands and the confidence interval expands. So every step ahead, the confidence interval expands. For MA model, your confidence interval is going to be also of the same of the same width. So this is not going to be expanding, this is going to be constant width, and the forecast is going to be also constant. So this is a very specific class of model with this respect, because, well, it is not that usual that time series are not developing, they are not showing some dynamics, they are not converging to mean like after some time, but they are just flat, and that's all. And the forecast error is also constant. This is not that usual. Well, and we reached the conclusion that fast. So what we need to keep in mind here, we build the confidence intervals on the assumption that the true model is known and the past observations are also known. But in reality, they are not. In reality, we estimate the model parameters. Therefore, the forecast uncertainty is going to be even larger than we have computed. So the uncertainty would be larger. This is very important to remember. The forecasts are always imprecise. They must be reported together with the confidence intervals. It's not like, next year GDP growth is going to be 4%. That's all. No, you need to provide the forecasts all the time, forecast confidence intervals all the time. And given that the forecast confidence interval are that poor quality, because, well, obviously this is a poor quality of the forecast when your confidence interval is from minus to large plus. Well, yes, in the long run, AR1 forecast converges to the unconditional mean that we have been discussing. So phi 0 over 1 minus phi 1. And the long run forecast error would also converge to the unconditional variance like this. But this is in the long run. So after a long period of time, it would converge. So for example, in our case, in the long run, GDP growth converges, GDP growth forecast converges to, and well, we need to compute this. We have all the estimates. This is 0.9353 divided by 1 minus 0.6162, which is what? 1 minus 0.6162. So reciprocal multiplied by 0.9353. So this is 243.69, something like that. So in the long run, the forecast converges to this, and the forecast variance converges to, so we need to take the forecast variance here in the numerator. So 23.5563, and here squared, right? So 0.6162 squared plus 1 reciprocal times 23.5563. So 37.9758. So the long run 95% confidence interval is, well, this is going to be mess, of course. But let's try to do that. So plus minus square root 37, 9758. 243.69 plus minus square root 6, 1624. Basically, this is gonna be 243.69 minus 6, 1624 minus 3, 7255 2 plus 43.69 plus 6, 1624 to 8, 59.93. So this is going to be the confidence interval for in the long run. Yeah. So that's basically all in general, in very general about forecasting. The logic is simple, and basically even people from school must be able to understand this logic. So finishing this lecture, you have quiz number 8. So basically 3 quizzes together. The quiz from the lecture from the last Saturday and 2 quizzes from today's lectures. But I extended the time for this quiz for you to have enough time for the preparation. And also there is going to be a home assignment number 7 with the estimation of linear models and forecasting available until December 8th. So you have plenty of time, 3 weeks, for finishing this home assignment. So you will have exercise sessions. You will go through the practical issues of estimation, forecasting, and so on. And I hope you are going to be ready to pass the home assignment number 7. If you have some questions while preparing for the home assignment, while making the exercise session, so please drop me a message. We can agree on some meeting, or I don't know, I can, if I'm able, I can respond to your questions just as the return email. Any questions to me for today?
No questions.
No questions.
Well, in this case, thanks for your attention. So the next Saturday we will have 2 last classes for the time series and for this course. Have a nice weekend and see you next Saturday. Bye-bye.
2 last classes, in general?
Yes.
Overall?
So we agreed that we are gonna kind of speed up doing 2 lectures every Saturday in order for not having classes in December, right? So there are going to be 2 last lectures, but not classes in econometrics, because you will have exercise sessions, of course, but 2 last lectures for econometrics next Saturday. Okay?
Okay.
Perfect.
I see now. Yeah.
Have a nice weekend and see you next Saturday. Bye-bye.
Goodbye.